Good morning, professors. Today's the oral defense of my master thesis degree is titled Quantum State Tomography with a Covariance matrix approach. So let's start. Okay, today I will walk you through some motivational aspect in the quantum optics field, going through some literature review, what we have done in the field, state the problem, to check some background information necessary to understand the research, and to go to the single mode state reconstruction and then to the two mode state reconstruction, and finishing with some comments on the conclusions and perspectives. Okay, so at the core of our discussion is the quantum optics field. This branch of physics aims to study the interaction of photons with matter and the quantum phenomena that emerge from these interactions. But for my thesis, I would like to align the purpose of the goals of my research with the interest of my research group. So in our research group, we have been recently focused on the quantum state generation of single photon state, coherent state, and lately squeeze states. The squeeze states has the interesting property that they exhibit a reduced uncertainty that we can use them to make very precise measurements. Together with this, we have some detection techniques, such like balance homodyne detection that help us to extract the information from the generation of the quantum state. And now, to make this have real applications, we have the need to research on a quantum state tomography method, which basically is the acting of reconstructing the information from the quantum state we are generating. Once we have mastered this, we can go to very cool applications because we are already able to create and characterize quantum states, so we can use them. We can manipulate quantum state to perform something like optical qubits in quantum computing and also in quantum information science, which mixes information theory with quantum mechanics. We can think about manipulating states to encode and transmit information through quantum channels, and this can be quite interesting. But recently, the squeeze state generation research is interesting mainly because of the gravitational wave observation. So I'll comment a bit about it. So we have, for example, a cosmic event as the collision of two black holes. We know by the predictions of the theory of relativity, we get some ripples in the space-time, and the information, these ripples travel across the universe, reaching the gravitational waves observatories, and they squeeze the light in the large interferometers. This is an example with the LIGO observatory, and here we have the result for the first detection of a gravitational wave in 2015. So they detect this in the LIGO with the two LIGO gravitational observatories. So they just show that we can use the study and characterization of the squid light can help us to get some information from the universe and understand a little bit more of this and other kind of very precise measurements. So I would like to reflect about the question if can we observe the quantum realm? So for this, I would like to share with you Plato's allegory of the case. I think is very suitable to understand this. So philosopher Plato said about the theory of ideas or theory of the forms. So there is a real world, and this real world, the real world object is lighted up by a fire, producing some shadow. So he says like the situation, there is a man in a cave, the man cannot interact with the outside world, he can just interact with the shadows that he sees on this world. I think something similar happening when we deal with quantum mechanics, because we have a abstract reality living in this framework that we can just access by means of the logic of mathematics, but our nature is not quantum, so we can just access to some projections of these quantum objects in their quantum realm that interacts with us. And the way we can use to get this information, it's quantum state tomography. So we have really an object that lives in an infinite dimensional Hilbert space, complex Hilbert space, but we can get some kind of prediction of this information in our world. And I would like to have this with the quantum state tomography to see that we can in some way observe this. The word tomography comes from when we think about going to doctor and we take a tomography of our body, of our brain to see what's going on inside. So basically, that's why we define as quantum state tomography the act of reconstructing a quantum state with some experimental measurement. Okay, so let's go through the state of the art. What have we they done on quantum state tomography. So first, the most traditional way to reconstruct quantum state is the maximum likelihood estimation. This is a statistical method that aims to reconstruct, find the better statistical distribution that better fit a statistical sampling. But in the other side, I feel proud that in my research group, we have some new ideas, some innovative ideas about about quantum state tomography. We have introduced the machine learning enhanced methods, and I can share with you two. One of them is density matrix reconstruction. So they use density matrix, they reconstruct density matrix to characterize the quantum state. And in the other side, we can also, there is another project on directly estimating the parameters that characterize a quantum state. So what are the disadvantage of this is this is slow, and this has not very good precision dealing with the squeeze states. With this, we have proven that we have a good precision, and also this can be performed in a single scan measurement. This, in other words, can take us to let's say to have a real-time tomography, which can be really interesting because having the tomography as we are generating the quantum state can be very practical, very useful for the research on the creation and the manipulation of the states. So inspired on these machine learning based methods, I would like to go one step further of this and propose what is the goal of my research. So let's state the problem. I would like to create a machine learning method that inputs experimental measurement and outputs the quantum state, but this quantum state is represented by the covariance matrix. So why I want to use covariance matrix. Later on, I will give you some good arguments to prove this, but so far I can share with you that covariance matrix representation is another way to see quantum state. We can have a simplified way to represent the state. So for single mode case, it looks simple, but when we really take the advantage of this representation is when we go to mouse states, because if we are computational physicists and we deal with inputting density operators and vectors of quantum mechanics in the computer, we know that dealing with big Hilbert spaces is complicated. And by joining Hilbert spaces to have a two-mouse representation can be a headache. So covariance matrix can offer another way that can make that much more feasible. Okay, so now let us go into some background to understand what is this research about. So first, let's talk about experimental measurement. So there is some experimental setup that we have performed in the lab. It's called the balanced homodynamic measurement. For this, we have two ingredients. First, a high amplitude coherent field or local oscillator field, and the field that we want to study. So when we make this suitable experimental setup, we can input the two fields. They go through a beam splitter, and at the end, we are measuring this difference in the photodetector. This will just count the number of photons that this detector count, like the difference of this. We can prove that measuring this difference is proportional to the value of the amplitude of the coherent field, the expectation value of the coherent field parameter, and the expectation value of the position of the coordinate operator. It has the subscript of beta because with this we can make we can range over all the phase space. So we will get this and we will try the measurement of, let's say, the picture of the quantum state. Just go from 0 to 5, and this has something of what's happening, we are covering here. We need a high amplitude coherent field because quantum effects are small, so we need to amplify them. We can see that the Bacon state holds a Gaussian form, and this is an experimental realization of the Bacon state in our research group. So I would like to simulate this. So I want to create a machine learning model, so I need a lot of data to simulate this. This experimental measurement. We will define this as a quadrature sequence. I need three things to successfully simulate the quadrature sequences. First, I need to know what size do I need to choose, because experimental measurement has an overwhelming number of 3.5 million points, so I need to downsample my data, and I will do it to 2048 points. Why this value? Because after different experiments, we have seen that this is the a small value in the data set that can still keep the Gaussianity, so it can still capture the essence of the quantum state. As additional to this, we need to take care about the truncation, because to simulate this, we are writing quantum state, and we know that we are writing with our state in a focus space, and we need to truncate because we are inputting this into the computer. So for different, we have seen that when we are simulating squeeze states for different squeezing levels, we need different truncations to get an accuracy sampling, an accuracy. In this case, the vector function, you see how you can look to the function as we increase the truncation in the focus specs. And as a third ingredient, I have we can take advantage of the symmetry that has the squeeze state, because if you see after a pi rotation, we still keep the symmetry, and if you see the quadrature value is a way to see the quantum state from the point of view of the center going like rotating from 0 to 2 pi, and we can see that there is a symmetry. So my quadrature sequence, I will simulate them from 0 to pi to take advantage of the symmetry. 2048 points in the phase to characterize the phase of the quadrature sequence, and setting a proper truncation for different squeezing levels. Okay, this is just to show that I can just, by writing the quantum state, I can write Wigner function and simulate a quadrature sequence. So this is just made for vacuum, thermal state, coherent state, and squeeze thermal state. Okay, now I would like to get into details about why it's good to use the covariance matrix, and I would like to do a formal introduction of it. So let us go through some mathematical notions. So I will introduce some symplectic geometry concepts. So a symplectic geometry, a symplectic manifold is a manifold that is even dimensional, is smooth, and additional has a symplectic form. Why this was what symplectic manifold can we find in quantum mechanics? Basically, the phase space and the commutator operators, the canonical variables in the phase space. So we can think of writing. Okay, we can think of an n bosonic system, so we will have 2n canonical variables that commutate themselves. Here, I will gather all of them in this vector of operators x1, p1, xm here. By taking the commutator between each of these components, I will get this in terms of this matrix. I will define this as symplectic form. What is the interesting thing about the symplectic form is a way to write the rules that the quantum mechanical system have. We know that each canonical variables respect some rules for the usual the canonical commutator relationships. So we are gathering all together here in the symplectic form. A good advantage of this is like when we are joining individual individual mode states, we do it by a direct sum. And at the end, okay, an additional to this, we can define in this context the symplectic transformations. And the symplectic transformations are special because we want that this symplectic form is respected, because the canonical commutation relationships are always respected. So this can be, for example, rotations or squeeze operators. So we need to ask for this invariance on the symplectic operators. Okay, beyond all this, we have seen that the phase space has a symplectic structure that is underlying with all these operators. So not for part of this space, but in the interaction with this space, I can define the covariance matrix, which only keeps the correlations between every one of the operators. And writing my state in this covariance matrix language, I can find the absurdity relation just like this. Just to compare what I mean by Hilbert space representation and phase space representation, we can just compare Hilbert space is infinite dimensional, phase space is just 2n dimensional. So when we have single multi-stage to multi-stage, can be so much simpler. And here is where in this mathematical structure, when we talk about the Hilbert space or the phase space, like where I can really take advantage of the covariance matrix. So for single multi case, maybe they have a similar difficulty or a similar complexity, but for the when we are joining two multi-states, that's one of the goals of my research, we do it by a tensorial product. And if you have written this in the computer, you know that this can be tensor product of two already truncated Hilbert spaces give a very complicated matrix, big matrices that can be a headache when we are computationally sharing a problem to solve. But by dealing with the phase space representation, we have just direct sum that makes the matrices so much simpler, representation so much simpler. And these are other analogous characteristics like unitary operators, symplectic transformations, so we can characterize this. My conclusion here is like covariance matrix is a suitable representation of the quantum states, and we can take advantage of that in our research. Okay, so once I have studied some theoretical ideas, let us go to the methodology and the results on the single mode reconstruction. But for this, I would like that we are able to understand what really we mean by single mode squeezing. So this is a quadrature sequence, as I told you before, for a squeeze state. We will consider a squeeze thermal states just by considering interaction with the environment. Here I'm plotting the covariance matrix curves. What this means, like basically for every point for the phase, in this case 2048 phase points that define my quadrature sequence, I have one covariance matrix related to this. So in order to understand what's happening to this curve, we can break down every term of the covariance matrix. So this is single mode covariance matrix. And we can see that every of these terms is in terms of the square of the creation or annihilation operators. And since my squeeze operator is in terms of this, we can see that they actually will squeeze. So the squeezing will be exceeded, like they will alter these terms. So their terms are basically a squeeze, as we can see here. And I would like that you see something interesting about this is like in the dashed black line is a special point because this curve is 0, this is minimized, this is maximized. Very convenient, right? So for this, okay, this is so far. Now let's go. Let me go to show you this before going into details. This is just a simulation of the experimental realization of this in the computer. So this is quadrature sequence. As here, I'm just increasing the squeezing level for 0 to 15, and this is what's happening in the Wigner space of the functions of this squeezing, and we can just see. This is a squeeze vacuum state. This is a squeeze thermal state for N1 thermal parameter. And this is like kind of thing what's happening. And in some way, we would like to be able to do this with the real-time tomography to see what's happening in the Wigner space while we're getting the experimental measurement. Okay, so I have some curves, right? But I have actually 2048 covariance matrices. I would like to find a suitable way to really represent and characterize my state. And for this, let us see something interesting. It's like, you remember I showed you like this point where this special thing happened. When we write it in the covariance matrix, we can write it like this. This is minimum, this is maximum, and this of diagonal elements are 0. So I can barely say that I can describe my state by using covariance matrix in this form together with the phase point that I'm getting in this form. And I want to show you that this is enough information to reconstruct the state. So in order to take advantage of the power that the symplectic structure of the space has, let us go to some symplectic geometry theorems. So Williamson theorem just states that we can have a covariance matrix or positive definite matrix, and by symplectic transformations, we can find a diagonal form of the matrix. In the case for single mode cases, we can find a diagonal form. So this theorem, what it's saying is like we can always find this form once we have covariance matrix. And the thing here is like the symplectic transformation that will take us to this form is the rotations, right? So that's why here I just want to show you that we can freely rotate until we choose the point. So we can always find this point, and this point will be the one which will characterize my state. So we can always find this form, and we will define this form as standard form of the covariance matrix. Okay, so how comes my methodology? So I would like to train my machine learning model with all the quadrature sequence that I have simulated in the way I explained before. I will build a machine learning architecture made of a one-dimensional convolutional neural network enhanced with ResNet to go to a deeper structure. And I would like to keep these covariance matrix conditions to respect these conditions. And at the output, I will output the elements of covariance matrix are the phase angle in which this happens. So I can reconstruct my state. So after some results, I can show you some benchmarking to show you that this method really matched with some experimental results. So first, when we have gone through the quantum state tomography techniques in our lab, we have plotted these squeezing and disqueezing curves, which tell us something about the loss of purity, because for pure state, they would follow the black line, like squeezing and disqueezing would be the same. But here we have an estimation. We have this curve because the states lacks purity, and our covariance matrix approach are the black stars, so they follow the trend. For this, the good advantage of this is like the anti-squeezing and squeezing level is in terms exactly of the minimum and maximum of the uncertainty, and this is basically in terms of the elements of the covariance matrix in the standard form. So it's very suitable to measure this directly. Additional to this covariance matrix representation, we can also get other things like, for example, purity. So we can characterize the purity of the state we have generated in the lab. So here there are just some trend curves. This is just maximum likelihood estimation, overestimates purity. But machine learning based methods, this is density matrix reconstruction, this is experimental fitting, and this is my approach. They follow similar trend. And at the end, I would like to benchmark with the fidelity. Fidelity is a way to compare how similar is one state to the other, right? So, but fidelity is in terms of density matrix, and the last benchmarking was done with fidelity. So I would like to build another machine learning model, a neural network that can go through the covariance matrix to reconstruct the density matrix to show that even though with covariance matrix I can get the information from density matrix, and once I get it, even though I have stepped through two machine learning methods, I can get high levels of fidelity. So machine learning methods reach a high level of fidelity if we compare to the maximum likelihood methods. So the good thing is like we can keep high levels of fidelity for high squeezing levels up to 10 decibel. So and here I just have to experimental reconstruction of the experimental realizations of the squeeze states. This is a low squeezing level state, and this is a high squeezing level, a high level squeeze state. What I can say here, okay, with my experimental measurement, I can perform an estimation over covariance matrix and the phase angle, and with this I can reconstruct the Wigner function and get some information like purity, squeezing, and disqueezing. And also something additional that this can do that the other methods cannot perform is the estimation over the angle. So here for low squeezing level quadrature sequence, we see that because of the symmetry of the quadrature sequence, it's hard to estimate the minimum value that we can, I don't know, we see that it's about here, but we can make some estimation. But for high squeezing level, we see that our quadrature sequence has a sharp form. So it's very defined for so we can estimate properly the angle. Okay, so far I have shown you some method that works to make tomography for single mode states. I have reconstructed and I have proven that they match with experimental results. But in our research,
I can interrupt you at this moment because you are going to two more. Yeah, the next one two more. So regarding the single mode, so how you deal with the mixed state, in particular impure squeeze state.
Impure squeeze state. Well, I think I write my states as thermal states.
Yeah, but if you go back to the previous.
Sorry.
Yeah, here. So as you can see, actually here you show I suppose the P should be the purity.
Yeah.
So you can estimate the purity directly.
Yeah, because there is a when we write by using covariance matrix representation, we can write purity, squeezing, and squeezing these things in terms of the covariance measure.
So if I understand correctly, if we go to the next slide, so from the experimental data, you have this 2x2 matrix. So you estimate from the diagonal terms about the squeezing and anti-squeezing. So this is what I know.
Yes.
So this is squeezing and anti-squeezing. And with this, the difference between squeezing and anti-squeezing, you try to estimate the purity.
Yes. The squeezing and anti-squeezing is a way to see the purity, because we can see with the other methods like this course, when we are increasing the squeezing level of the states, there is some interaction with the environment. So the anti-squeezing doesn't really increase same as the squeezing. So in some way, when we are applying a very strong pump power to generate the state, they don't behave like purely. Yeah, that's the thing. So the way I can relate about this is by measuring purity and by measuring squeezing and anti-squeezing. We can directly estimate it from maximum and minimum values of this. This can basically the terms of the covariance matrix in the standard form. So we can directly estimate all this from the covariance matrix. I would like to, I have already performed this for single mode states. So in the group, we are planning to make the experimental realization of the two modes state, but so far we haven't done it. So I would like to address to this problem, even though we don't have experimental results, but we can propose some ideas that can help maybe to our group to reach these results. So for this, I was thinking that, okay, we need to really think how to perform this, because there is not too much in the literature about this. So let's see what's the solution for this. So in order to address this problem, I would like that we understand the two-mode squeezing. So for the two-mode squeezing, this is the two-mode squeeze operator. It's mixing the two individual modes, creation and annihilation operators. So in order to do a similar analysis to what we do for single mode states, this is the two-mode covariance matrix, and these are every individual term of the covariance matrix. But notice something interesting. When we talk about the squeezing, we have these terms, and the terms that are being squeezed are here, the green and the yellow components, so the off-diagonal block components of the covariance matrix. Not here, not here, not here. What this means, like the two-mode squeeze operator won't squeeze in the individual modes. So when we are trying to think about these, the individual modes, and we apply two-mode squeeze operator, they won't really change. They won't really be squeezed. So what's really happening, they will be squeezing the correlations, and that's really what makes them interesting, and that's what actually makes them be entangled. So these off-diagonal block components are just the correlations, and for example, correlations x1, x2, p1, p2. So the information about the squeezing will be stored here. And so for this, I would like to think about how can I capture this SM, because if I think about individual modes, they cannot really capture the squeezing. So how can we perform the experimental measurement? So what's my proposal? My proposal is to think about the superposition quadrature. We define this operator as the superposition quadrature of the individual quadratures. Why I propose this? Because when we measure the uncertainty of this, we see that this term actually will be squeezed, because it's in terms of the terms that will be squeezed by the two-mode squeeze operator. So the thicker curves are the curves measured with these superposition quadrature operators. I use these curves to create the quadrature sequence. So my proposal for the experimental realization is like we superpose the fields, and we can simulate the quadrature sequence with the superpose operators. For this case, I know there are many curves. I hope it's not too confusing. I plotted the curves for covariance matrix curve for every of the components. We can see these constant curves just represent the single modes, the individual modes that don't be squeezed, but these oscillating curves are the correlations that are actually being squeezed. And in an analogous way to what we did in the last case, we can see that when we increase the squeezing level, this is what's happening. Thicker curves are the curves for the superposition quadrature that will define the quadrature sequence. And these oscillating curves are the curves of the covariance matrix. In a similar way, as we see before, there is a point in which we can conveniently find this vanishes here, this gets its minimum, this gets its maximum, this gets also a minimum. So we also have some analogous idea to what I said about the standard form. Okay, so this is the simulation of what's happening here. But this Wigner space is the Wigner space in the superposition quadrature. This is actually the real interesting Wigner space. We know that if we are dealing with two-mode states, we have four-dimensional Hilbert space. So I think here we can really see the essence of what the two-mode squeezing is doing. So we can see that for the x1 p1, x2 p2, and this like x2 x2 p1 and x1 p2, we can see that they don't get a squeezing, but in this, which are the correlations p1, p2, x1, x2, they are they undergo this squeezing. So this just is in some way entangling the state, and so the information about these states they get entangled, and it's because the squeezing, this information, the squeeze operator is affecting these pairs, the correlations. Okay, so I would like to take advantage also of the symplectic structures. There are a lot of properties. Proof of these are references in my thesis document. So for this property, I can tell you that for a two-mode covariance matrix, if we transform under symplectic transformations, we can also find a standard form. And this standard form has the following form. We can just do this. Here, in this case, we can do it for local symplectic transformations. So these are basically rotations of the two modes. So after rotating, we can find suitable form to represent my state. A two-mode state now is represented with 3 parameters, which makes the description so much more simpler and suitable for our description. So going into the methodology for this, okay, how do I? This works in an analogous way for a single mode case. I will build my training data set. For this, I will join the Hilbert spaces, and I will make these simulations with the superposition quadrature operator. I will be in an analogous way machine learning model with one-dimensional CNN enhanced with ResNet, and respecting the uncertainty conditions on the covariance matrix, and I will output the phase angle together with the estimated covariance matrix, so I can estimate the 4-dimensional Hilbert space that is characterizing my two-mode states. So far, we don't have any experimental realization, but this is just as a simulation. I can just randomly simulate two-mode squeeze states quadrature. These are covariance matrix curves, and I can just reconstruct the covariance matrix with the estimated angle and reconstruct a 4-dimensional Hilbert space. This is just proof that I can do it in a single scan measurement. So one of the final things that I would like to comment is like the interesting thing is about two-mode states is that we have entangled states. Using entangled states is very suitable to do quantum communications, to perform optical qubits. So a lot of very interesting applications. So we would like to characterize this entanglement. So for this, I will introduce like 2 ideas. The first one, range to entropy. So basically, is the entropy for one state, for a state defined by the density matrix, and we can write this conveniently in terms of the covariance matrix. And additional with this, we can define the range to mutual information. What is this doing? Is gathering the information related to the entanglement. So how strong is this entanglement? How strong is the communication between the two modes? This can be characterized by this. There are many ways to measure entanglement. This is just a way I found suitable because I can find a representation in terms of covariance matrix. So by using the very suitable standard form for the two-mode states, I can find that my matrix, my range to mutual information is dependent just on the C parameter. And my proposal is that once we can characterize the entanglement from our lab, we can plot some entanglement curves with this range to mutual information, which the behavior is something like this. So if you see, the entanglement information will be stored in these correlations in this for this parameter. Okay. So and as you can see, we don't have A or B for the for this entanglement information because entanglement information is not there, but is in the off block diagonal terms. So for the state that I just reconstructed, I can estimate just made some estimation about the longitudinal information. So that's something that we can do once we have some experimental measurements. So as conclusions, I can say that machine learning enhances quantum state tomography by using covariance matrix. It's efficient, precise, and fast because it can perform single star measurements. So we can we can think about the idea of a real-time tomography. That it can be done, it cannot be done with other methods that are not machine learning based. Also, covariance matrix representation can avoid loss of precision from truncation in the fog basis, and it can store the information in a smaller matrices that can fully capture the essence of the quantum state. For the single mode squeeze state reconstruction, we can say that it accurately reconstructs the single mode squeeze state. We are able to estimate binary function, purity, squeezing, and de-squeezing with high fidelity level. Once we have made that this works here, we can think that it is promising for a future two modes implementation. So we can propose a two modes tomography method that can perform a reconstruction that can simplify the complex structure that it would have if we are joining Hilbert spaces in the fog space representation, and we can have a more reliable or tractable way to deal with this tomography. As prospects, I would like to implement, in the group, we would like to implement some of the machine learning based methods for gravitational waves detection. Because reconstructing the information from the squeeze states that detect the gravitational wave can tell us some information about the gravitational wave. Additional to this, we can perform real-time tomography by reconstructing covariance matrices in FPGA devices. These devices are programmable devices, and the covariance matrix model is lightweight, so it can be suitable for this. And in the future, we would like to compare with the experimental future realization of the two-mode squeezing in our lab. As an additional information, for the first stage of my thesis, I participated in the physics department poster competition. I got first place with the first stage of my thesis, and I also was finalist in the 3-minute thesis competition with the talk, reconstructing the quantum realm. Thank you.
Okay, thank you. Okay, now the presentation is now open for question with the president. We want to start first. So start first.
Let me ask first. Okay. So yeah, I'd like to ask. So when you do because you need to generate the data for the simulated data for training the model. So what I want to ask is, when you generate these simulated data, did you consider any kind of like noise?
Noise. Okay. We can think this problem with two ways. First, we can think about the ideal problem of we don't have noise and we have purely Gaussian states.
Yes.
We can do this. That's what I did. So I've been also discussing about or thinking about how can we implement some noise.
Yes.
So there are some words that they aim to describe the tomography for non-Gaussian states that are included in noise, but actually we can do something similar because we can simulate our data, and additional to this, we can include that non-Gaussian noise in the simulated data and try and perform this with the tomography. So I think tomography is able to do this. I didn't include it in my case, but I think if we see that the noise is a problem and we need to consider, we can simulate data, adding some noise, some non-Gaussian noise, so it can maybe represent a reality a little bit more.
Yes. So I'm asking this is because when you're doing measurement, you're using some instrument, right? And then so that definitely will have some limitation of those instruments, where like there will be some kind of noise that associate with those.
Yes, and I think this is one of the main problems that maybe the experimentalists have dealing with this, with the loss of the coherence, with the interaction with the environment, with these things that makes that the measurement like have this like problems, but so far, when we are considering that the states are thermal, at least this is enough to characterize the states. But if we think that we need to include noise, we can simulate the data adding noise.